Hey guys, what's going on? So today we're going to continue with statistical field theory. I realize some of the topics that I've been covering in the past I've sort of let go of a little bit. I haven't really let go of them. It's just things have been a little bit busier than I anticipated, and so getting this content out has been a little bit challenging, but getting back into the swing of things. So in this video we're going to talk more about statistical field theory, and we're going to start bringing ideas together, bringing new ideas together as well to learn this topic, okay? Because we've now sort of talked about probability distributions, we've talked about moments, we've talked about the Ising model. Now we're going to come at this from those were sort of introductions to those topics. Now we're going to go forward with this. We're going to talk more about statistical mechanics and then statistical fields, okay? So in order for us to understand statistics, so again, this will be free. Again, this video will be free. Make sure to hit that like and subscribe button if you want access to exclusive content. You can go onto Patreon as well to access exclusive content. So let's get into this now. So we're talking about statistical field theory, but there's a lot of sort of prerequisites into understanding statistical field theory, one of which is non-equilibrium thermodynamics. And really what this is it's the study of thermodynamics when we're not in equilibrium. But what exactly does that mean? What does non-equilibrium mean? Well, non-equilibrium, I think, can best be introduced to us just by looking at this diagram here. So this diagram, this really exhibits a system. It shows a system that eventually gets to equilibrium, which is how most systems really work, right? The systems start in some chaotic phase, but then quickly go to equilibrium, right? If you're looking at a chemical reaction, for example, there might be some initial phases or initial steps that the chemicals have to go through before you get a balance of stoichiometries, for example, okay? And this is the non-equilibrium part. There's like right here is the non-equilibrium part, and then this here is the equilibrium part. And this is where most of your understanding, when you go through undergraduate, for example, undergraduate courses, most of statistical mechanics, most of thermodynamics studies systems when they're in this phase. But there's this whole phase right here that is non-equilibrium that is not covered as much. It's more of a graduate topic. But this is what we're going to dive into for the next couple of videos, because I think it's important to understand this when we start talking about field theories as well. Because a lot of the concepts we introduce when we start talking about this are going to be reintroduced when we start bringing the language of fields into things. So let's begin to dive into studying this domain of non-equilibrium thermodynamics, which will be a pivotal in understanding statistical fields. So we're going to start with defining a state variable for our system. So a state variable, okay, so we have the state of our system can be labeled like we do with pennies, for example. We label heads and tails. But if a system has many states, say n states, well, it's going to have a state labeled 1, state labeled 2, 3, 4. These are really just labels that we put on the states, okay? So, and our system can be described as a trajectory in this state space, okay? From time 1 to time n or whatever, okay? Little n, or I in this case. So a trajectory can be written v, or whatever you want to call it, but I'm going to call it V in these videos. A trajectory can be written in this way, where we have sequential y1, or y0, y1, y2, y3. These are all values. These are all the numbers that identify the state of our system. So we start here at state 2, then we jump to state 4 or whatever, and then we go back to state. This looks like 5, 4, and then jump up to state n. Okay. An ensemble can be thought of as a collection of experimental runs. There are two broad types of ensembles, pure ones and mixed ones. So this is just some vocabulary. Pure ensembles are prepared in the same state. So everything that starts at the same state. So I don't know, I have 2 pennies, for example, both of which start at the head state before I toss them. Something like that. That would be an example of a pure ensemble. Mixed ensembles are ones where you are prepared in not the same state, right? This was a typo. Mixed ensembles are prepared in not the same state. Actually, I'll do not the same state. So here we have looks like state n minus 1, and then here we have state 2. Okay. So this is just some vocabulary. We want to keep that in mind. All right. We want to ask the question, what is the probability of getting some sequence of states? In other words, we are looking for a probability of having a particular sequence of states, which is V. Okay. The properties of such an equation consist of the sum over all possible trajectories equaling 1, because this is how probabilities work. Right, so the probability of this trajectory is the probability of all these with y0 going from 1 to n, it should be y1 going from y to n, and y2, 3, 4, 5, however many y's we have, right? Again, the y's are the stops along this system, right? So I like to think of this as every time we stop, at every time point, we're integrating. So we integrate over all these states, or we sum over, right? In the discrete case, we sum over. So we sum over this guy, and sum over this guy for a particular trajectory. And that all has to equal 1 because this is a probability. The physical quantity associated with the state. So we have some trajectory there. We can attribute some quantity to this trajectory, like an average energy, for example, to this trajectory. Well, the average energy is going to be the probability. We've seen this before. We've seen this before in our first few videos where we talked about this. But when you sum over this argument, and this is a probability, the average is just going to be this times this, and that gives us the average. Okay. So this is an energy associated with a particular trajectory times the probability of that trajectory. Gives us the average over all trajectories. When calculating the probability of such a trajectory, we are going to assume Markovian dynamics. So this is the first time we're talking about Markov now. So Markovian dynamics. This is the idea that the state of a system really only depends on the state of the system that it was 1 unit of time before that, not 10 units or 20 units or so forth. It only remembers what was right before it, and that was it. That's it. So that's what Markovian dynamics really is. It's this idea that why we're asking the question, what's the probability of y plus 1 given all of y0, all these values up to yi is equal to the probability of I plus 1 given that our previous step was just yi. So we ignore all these guys up until yi. Okay. And so to calculate this probability, all we need to do then is compute the ratio, right? So the ratio of this guy to this guy, right? This is to I plus 1, this is just to I, is going to be this, right? So that's how we define that probability. It's just a ratio. Well, we can multiply both sides by this, which is right here. And then we can say, well, the probability of this trajectory, we'll call that V. As we said before, this is this trajectory going to I plus 1. Okay. is equal to this times this. Well, this is just a recursion formula. We can realize this because if the probability of going to I plus 1 is all of this, where we have the next one down is right here, right, yi, well, the probability of yi then is going to I minus 1, which is right here. Okay, so the probability of, so we can rewrite this, right? We can rewrite and we could say the probability of, right, so this should actually be y0, of y0, y1 to yi is equal to the probability of yi times the probability of y0, y1 dot to yi minus 1, I minus 1. But then we can make an equation for this just like this, right? And so this is a recursion formula. This is what we're saying here, is that we can break these up into smaller probabilities. Okay, that smaller probability, and when we do this recursively, we get this, and then we can do the same thing here. This is really just j plus 1 to j, where j is going to go from 0 to I, okay? Because we want I plus 1, so I plus 1. And so if j is equal to 0, this is 0, this is going to be 1. If j is 1, this is going to be 1, this is going to be 2. So these are probabilities that jump from between states, if you will, multiplied by our initial probability. So we could take each probability on the right-hand side of this equation, equation 2 here, to be elements of some larger matrix that we will call our transition matrix. So our transition matrix is W n I plus 1 n I. So this is how usually when you read physics or math stuff, you're reading in this direction, which is weird, but that's how it works. We're going from I to I plus 1. Here we're going from I minus 1 to I, and we're going from n to n, or n naught to n. Okay. And in doing that, the state of our system, so we can draw our trajectory again, and each red arrow here is essentially the probability. It's a probability of going from each step to each step. Okay. This is useful to write this in the matrix way because, as we'll see, we will then start to develop constraints on Markovian models. Okay, so let's recall a fundamental probability, a property of probabilities, which is all the probabilities have to add up to 1. Right? So P, the probability of A given P, sum over all A, again, sum over that vertical line on our diagrams equals 1. In the language of non-equilibrium statistical mechanics, this means that the probability of getting any state after some other state immediately before it is 100%. Right? So the probability of W m to n at some time, well, that's going to equal 1. Right? So if we're going from 2 to 3, and we're summing over all 3's, that has to equal 1. Because we're summing over all n's. That's what this formula is looking at. So so we have to sum over all of these coming from 2. All right. In matrix terms, this translates to all the columns requiring to add to 1. So we start at some initial state 1. We go to, say, state 2, This is just an example matrix, but here we're saying if we go from state 1 to state 2, the probability of doing that, of making that transition, is given to us right here. And if we say that the probability of going from 1 and then staying in 1 is 90%, well, that means the probability of going from 1 to 3 has to be 0%. Okay? And so this is 0.9, this is 0.1, that adds up to 100%, so this has to be 0. Okay? So all the columns have to add up to 1. That is what this thing, this property demands of these transition matrices. So this translates in a picture. This is how when we start talking about Markovian diagrams, we go from state 1, state 2, state 3. If we have a 0.9% chance of going from 1 to 1, that's just staying in 1. So this is that 0.9 chance. We have a 0.1 chance of going from 1 to 2. Well, that's this jump right here. So that's a 0.1. We have a 0.2 chance of going from 2 to 1. So that's right here. And you can see how this works, right? So we can consider all possible trajectories that start with state 1 or state 0. Okay, we're starting with starting with state 1, right? At time 0. So state 1 going to state 1, well, that's 0.9. State 1 going to state 1 again, well, that's 0.9. 0.9 times 0.9 is 0.81. Okay, so over 2 time steps, we have, if we're going from 1, if our trajectory is 1, 1, 1, the probability of that trajectory is 0.81. All right. If our trajectory is 1, 1, 2, all right, so 1, 1, 2, that's 0.9 times 0.1 is 0.09. If our trajectory is 1, 2, 1, so 1, 2, 1, well, 2, so 2 to 1, that's 0.2. So that's 0.1 times 0.2, that's going to be 0.02. And so forth, right? So the probability of all of these possible trajectories, okay, going from 1 to 2 to 1, going from 1 to 1 to 2, 1 to 2 to 1 again, and then 1 to 2 to 2, and then 1 to 2 to 3. All of these, when we add these up, these have to equal 1. All right. So if we start in state 1 and we operate on this state with the transition matrix, we get this. So we're starting in state 1. We have 100%. This is 100% probability of being in state 1. Well, when we operate on that state with the matrix, we get this. So now we don't have a 100% chance of being in state 1. We have a 90% chance of staying in state 1, and a 10% chance of being in state 2. Operating again, well, we have this. This now becomes a little bit weird, right? Because 0.9 times 0.9 plus 0.2 times 0.1 plus 0.7 times 0. That's when you do the math, you get this factor here. So as time progresses, we can think of this matrix as constantly updating the previous state or the final state. So one question that we might ask then is, does this final state converge to a constant vector? And if so, is the final state unique to the matrix that is and is such a stationary state guaranteed? So given some matrix, right? So if you're bouncing between trajectories, and you have some matrix that's doing that bouncing, given the matrix, all the entries in that matrix, can we determine what the stationary state of that matrix is? Okay, and the answer to that is going to be in, you might have guessed it, eigenvectors and eigenvalues, but we're not there yet. Again, I don't want these videos to be too super long, so we'll talk about that in the next video. But the answer is going to be yes. We're going to have to assume a few things, ergodicity and so forth. We'll talk about those concepts. But the point here is that when you have a path, you can assign, you have a matrix, okay? When you have a matrix, you can determine what the stationary state of that path, of that system is, okay? So that's associated with the eigenvalues of the matrix, okay? In other words, the equilibrium state of a transition matrix is an eigenstate of that matrix. So in the next video, and what we're saying here is that, is there a state such that when we operate on it, we get the state back, right? That's no, in other words, there's no longer any updating, okay? We've finally gotten to the state in which nothing's going to change anymore. So in the next video, we're going to see how we can calculate such an eigenstate. We're going to see how it can be unique, and yeah. So with that being said, make sure to hit the like and subscribe button, and I'll see you guys in the next video.